Dear students, I welcome you back to the session 4 of multiple integrals. Quickly we recap the sessions third, that is the last session. In the last session we did the evaluation of double integrals by changing the order. Means there were two types of regions, type 2 region and type 3 regions. We can evaluate the integral by changing type 2 to type 3, or we can evaluate the integrals of type 3 by changing into type 2 region. So this process we studied is known as the change the order of integration. And also we discussed the change of variables in double integrals. So we have the Cartesian coordinates x and y changing into, there is a particular case changing into polar coordinates. The reason was it may be difficult to evaluate the circular of this type shown in the picture or region between the two circles. In such cases the simplification may be complicated. So we need to change into polar coordinates. That becomes simpler. So in this today's session we discuss the examples on changing to polar coordinates. So this is the one example stating that find the volume of the solid bounded by the plane, that is z equal to 0, and the paraboloid, its equation is z is equal to 1 minus x square minus y square. You can see the diagram here. This is the equation of the solid, diagram of the solid. Z is equal to, it is a paraboloid equation, z is equal to 1 minus x square minus y square. The question asked is find the volume bounded by the plane z equal to 0. Z equal to 0 is the xy, it is on the xy plane, and the paraboloid, it is bounded by the paraboloid. So inside that volume we have to find. So if we put z equal to 0 in that equation, what happens? Z equal to 0 in that equation of the paraboloid, we get, when putting z equal to 0, we get x square plus y square is equal to 1. So putting z equal to 0, you can see what is the equation in, what is the figure in xy plane. So x square plus y square equal to 1, it is clearly a circle. It is the equation of the circle centered at the origin and its radius is 1. So putting z equal to 0, we got what is the equation on the plane xy. This means the plane intersect the paraboloid in a circle here, z equal to 0. This represents the circle here. So the solid lies under the paraboloid and above this circle. We need to find the volume of that solid. So I am changing the Cartesian coordinates into polar coordinates. As we know that already, the relation between Cartesian to polar, x is equal to r cos theta, y is equal to r sin theta. We can prove this also, x square plus y square is equal to r square. So the region D is given by, it is a circular region, one can easily find it is a circle, its radius is 1. So r range is 0 to 1. The radius of the circle is 0 to, that is 1, means the limits of r are 0 to 1. And what about other variable theta? It is a circle, one full circle, the theta range is 0 to 2 pi. One can easily understand theta range is 0 to 2 pi, r range is from 0 to 1. So that is the region D in the xy plane. So it is defined, r varies from 0 to 1 and theta is 0 to 2 pi. These are the limits of the integration. Since the equation given z is equal to fxy, that is, that also we convert into the polar coordinates r and theta. So fxy is given, it is a paraboloid, 1 minus x square minus y square. Substituting x square plus y square, we know already it is r square. This becomes 1 minus r square. So fxy also converted to in terms of r. Now the volume formula we know that it is the double integral over the region R fxy dx dy. So, the region R, that is the D here, not R, R is the region in the Cartesian coordinates. So, D we have transformed to the polar coordinates. So, its limits are theta equal to 0 to 2 pi and R equal to 0 to 1. Now, fxy is changed to function of R and theta, that is 1 minus R square, and one more thing, dx dy we have studied in the last class, Jacobian into R dr d theta. So, Jacobian is R dr d theta. So, dx dy is replaced by R dr d theta in polar coordinates. Okay. Now, integrating one by one. Here it is a function of R only, there is no theta here. So, we can separate the limits of theta and R. There is no theta involved here. We can integrate separately with respect to R and with respect to theta. So, theta equal to 0 to 2 pi d theta is taken, d theta, and R limits are 0 to 1, integrating. So, this is simplified, multiplying by R into 1, R into R square, it is R cube dr. So, d theta is taken here. Now, integrating this with respect to R. So, the integration of R, so already this 2 pi is written, the integration of d theta, there is a constant here, integration of d theta is theta, then substituting the limits 0 to 2 pi, that is 2 pi minus 0, that becomes 2 pi. So, value of this first integral is 2 pi, it is a constant. Then the second integral, R integration is R square by 2 minus R cube integration, you know that R raised to 4 divided by 4, then put the limits 0 and 1. So, 2 pi into, simplifying here, R is equal to 1, it is 1 by 2, minus R is equal to 1, it is 1 by 4. So, 1 by 2 minus 1 by 4, it is 1 by 4. So, 2 pi into 1 by 4, it is pi by 2. So, volume of that solid is pi by 2. Suppose instead of converting to polar, we had used the Cartesian coordinates, what happens? You can see, without using the polar, as usual the earlier methods if you use, V is equal to double integration R. This is the function fxy is given, paraboloid 1 minus x square minus y square dx dy. So, the region R in the Cartesian plane, it is a circle, R in the Cartesian plane, it is a circle. Here its limits are, circle limits are, x varies from minus 1 to plus 1, is a circle, x square plus y square. The limits of the circle are in Cartesian, x equal to minus 1 to plus 1, and y limits are functions of x, that is y square is equal to 1 minus x square, then y is equal to plus or minus under root 1 minus x square, means the lower limit of y is minus under root 1 minus x square and upper limit of y is plus under root 1 minus y square. So, this is our volume double integral. So, minus 1 to plus 1 minus 1 minus x square under root 2 root 1 plus x square. So, we need to integrate first with respect to y, then substitute these limits, still a complicated expression, then integrate with respect to y, then substitute this. So, it is not so easy simplification, that is why we referred Cartesian to polar, then it becomes so simple integration and getting the answer here. So, that is the reason whenever we have the region in the xy plane is a circular region or part of a circle, you go for changing to, it is an advantage to change Cartesian to polar coordinates. So, you look into another complicated example here, shown here in this problem. It is again finding the volume of a solid, you can understand the statement here. Find the volume of the solid that lies under the paraboloid. Again the paraboloid equation is z is equal to x square plus y square. So, on the z axis you can see the paraboloid, it is above the xy plane, it is there, it only taken positive x axis. So, above the xy plane, and the inside the cylinder, there is a cylinder equation x square plus y square is equal to 2x So, another diagram which intersects with the paraboloid is a cylinder, you can see here. The question is, find the volume of a solid lies under the paraboloid, below that paraboloid, above the xy plane, this part, and inside the cylinder. So, outside what you are seeing, this portion volume we have to calculate. So, we have the surface equations, one is cylinder, another is paraboloid. We have to set up the integration limits here. How to set up the limits? The solid above the disc D, D means this one is a D, it is taken the xy plane, that is the circular base of the cylinder it is. This is the circular base, it is a circle, base of the cylinder is circle, it is on the xy plane, it is on the xy plane. And what is the center here? Center of this circle is not the origin, it is lies on the x axis. So, as per this, x square plus y square is equal to 2x, it is the equation of the circle. Equation of the circle, one can write its center is 1 0 passing through the origin. So, x minus 1 whole square plus y minus 0 whole square is equal to 1 is nothing but x square plus y square is equal to 2x. So, it is a circle, center is 1 0 and radius also 1, it passed through the origin here, it is passing through the origin. So, it is the base of the cylinder. So, the problem is above this, above the xy plane has a circle, find the volume above the xy plane, below the paraboloid and inside the cylinder. We have taken the base of the cylinder as a circle. Now, I am changing to polar coordinates because our region is a circle here. So, we need to change polar, the simplification becomes easier. So, in polar coordinates we know that x is equal to r cos theta and y equal to r sin theta. They are the relation between Cartesian to polars. If you square and add them, x square plus y square is equal to r square, you will get the equation. And substituting x square plus y square is equal to r square and another equation x is equal to r cos theta in this circle equation. So, that the boundary of the circle becomes, substitute here, r square is equal to 2 into r cos theta, r square is equal to 2 into r cos theta. The circle equation is reduced in terms of polar, r square is equal to 2r cos theta. So, 1 r get cancels here. So, it becomes r is equal to 2 cos theta. So, in polar coordinates r equal to 2 cos theta represents a circle, it is circular disc, D is given by its limits are. In polar coordinates we need to find what are the r and theta limits here. So, r limit is given, r equal to 0 to r equal to 2 cos theta. Then the theta limits, in this picture you can see it is ranging from minus 90 to plus 90. You can verify here, when theta equal to minus 90, if you substitute here 2 into cos minus 90, we know that cos 90 is 0. So, theta is minus 90, the value of r is 0, means radius is 0, that is the origin. This is the point for the lower limit. And theta equal to plus 90, theta equal to plus 90, cos 90 is again 0, even for one cycle minus 90 to plus 90, again the upper limit also 0, r equal to 0. In between you can check how to get r equal to 2 here. So, this is the angle theta equal to 0. So, there is a limit from minus pi by 2 to plus pi by 2, in between 0 is there. When theta equal to 0 you substitute here, cos 0 is 1, so r equal to 2. So, this is the r range. Even in between also you can check, between minus pi by 2 to theta equal to 0, there is a minus pi by 4 you can see. Minus pi by 4 if you substitute, 2 into cos of minus pi by 4 is cos pi by 4. It is 1 upon root 2. So, 2 upon root 2. So, r value is root 2. So, this length is root 2. R means it is length of the radius vector. So, r is root 2 at this point. R is 2 at this angle. So, r is again root 2 at the theta equal to pi by 4. R equal to pi by 2, it becomes 0. So, to trace this circle, what are the theta limits, that is theta equal to minus 90 to theta equal to plus 90. So, these are the limits of the integration in polar coordinates. Now, use those limits. The reason x square plus y square dx dy is given. Changing to polar coordinates, so theta limits are minus 90 to plus 90 and r limits are 0 to 2 cos theta, and also change the function. The function fxy is x square plus y square. You convert this in terms of r and theta. So, we know that x square plus y square is already r square, that is substituted here, and dx dy, this also we know that Cartesian to polar, the element dx dy is r into dr d theta. So, r is the Jacobian value. So, now simplifying this integral, so r square into r, it becomes r cube, r square into r, it becomes r cube. Now, integrating r cube, integrating r cube is r raised to 4 upon 4, r raised to 4 upon 4. Now, substituting in place of r 2 cos theta. So, r raised to 4, r is 2 cos theta, means 2 cos theta raised to 4. 2 raised to 4, it is 16. 2 raised to 4, it is 16, divided by 4 is there. So, the constant 4 is taken outside. Next, cos theta raised to 4, it is written here, cos theta raised to 4 d theta. We have to integrate with respect to theta. Now, we can change this minus pi by 2 to plus pi by 2. We know that whenever it is an even function, we studied even and odd function, cos theta is an even function, even cos raised to 4 is also even function. So, we can change this to the 2 times the half of the limits. There is a property of integral, whenever the function is an even function, we can write 2 times the half of the given limits. So, 4 into 2, its value is 8. So, minus pi by 2 to plus pi by 2 is written as 0 to pi by 2, that is half of this range here, 0 to pi by 2. Now, using the reduction formula, you studied already reduction formula, n equal to 4, you can substitute. Using that, the volume of the solid is 3 pi by 4 it is. You can see here in the demonstration, the volume element, volume under the surface, that is paraboloid above the xy plane. You want more clarity, you can see the live demo of that example. Using the software GeoGebra, we plotted in that software. This is the circle we shown in the figure. Circle, its center is 1 0 and the radius is 1 here. So, r equal to maximum 0 to 2. This is the circle that we have considered the base of the cylinder. Now, if I move this, moving means the integration, this is one strip integration with respect to, I am talking about the Cartesian here, this is a Cartesian circle, integration with respect to y, you will get here in the picture, you can see here, there is a plane region, we explained in the double integral many problems. This is once you integrate with respect to y, you will get a plane area under the curve, where curve is on the surface z equal to x square plus y square. Now, the second integration, if you move that, covering that plane area to the entire, that completes the double integral here. You can see the volume. So, that is the volume of a solid below the z is equal to x square plus y square, above the xy plane, inside the cylinder. So, this portion, the green color portion, that is the volume of that particular example. Now, moving to the applications of double integrals. The double integrals have a large number of applications, some of them are written here. If the function value fxy is equal to 1, already we discussed this one, fxy is equal to 1, then the double integral over the region R dx dy gives the area of that particular region R. That we also discussed, is it the area of that region. And second one, if z is equal to fxy, that is positive, greater than or equal to 0, it represents a surface. Then the double integration of fxy dx dy, this gives the volume of a solid. We discussed in many examples the volume of a solid that lies above the rectangular, above the region R and below the surface Z. Coming to the particular applications, when fxy is the density function, rho is a function of xy, be a density function, that is mass per unit area of the distribution of mass in the xy plane, then you denote m is equal to the double integration of fxy over the region R dx dy gives the total mass of R. This is an application formula. It is just integrating the function dx dy that represents the total mass of R when the density, that is fxy, is the density function is given. Similarly, fxy be a density function, rho is taken here, then x bar is denoted as 1 upon m, the double integration x into fxy dx dy. So, the density is multiplied by x here, fxy into x dx dy, then that is multiplied by 1 upon m. M is the mass per unit area, it is, sorry, m is the total mass of R. So, 1 upon m is calculated from the previous formula, then x bar is this one, x into fxy dx dy. Similarly, y bar 1 upon n, y into fxy dx dy. This gives the coordinates of the center of gravity. These are the coordinates of the center of gravity of the mass m in the region R. And also fxy is rho, that is a density function, then denoting Ix, that is the double integral y square into fx. Function is multiplied by y square, then integrated with respect to xy. Similarly, another one Iy, x square into fxy dx dy. These two gives the moment of inertia of mass in R about x axis and y axis respectively. So, Ix and Iy gives the moment of inertia of the mass in R about x and y axis. Whereas adding them, I0 is equal to Ix plus Iy is called the moment of inertia of mass in R about the origin. So, these two are about x axis and about y axis. Adding them, you will find that is the moment of inertia in R about the origin. Similarly, Iy is x minus a whole square into fxy dx, and Ix is y minus b whole square into fxy dy. These two gives again the moment of inertia of mass in R about the lines x equal to a and y equal to b respectively. The previous formulas about the origin they were, these two are about the lines x equal to a and x equal to b. And another formula 1 upon a fxy dx dy gives the average value of the function fxy over the region R, where a is the area of that particular region. So, you can use all the formulas for particular problems. Now, I take one example on application of double integrals. This example stating that find the mass and center of mass of a triangular lamina with the vertices given 0, 0, 1, 0 and 0, 2. If the density function is like this, 1 plus 3x plus y. The question is find the mass and the coordinates of the center of mass. So, this diagram is obtained from the vertices. You can see 0, 0 is the origin and 1, 0 is a point on the x axis and 0, 2 clearly it is a point on the y axis. So, using these 2 points we can find what is the equation of straight line. You studied in PVC classes. Find the equation of straight line joining 2 points. Say x1 and y1 is one point, x2, y2 is another point. What is the equation to find the straight line? y2 minus y1 upon x2 minus x1 is equal to x minus x1 upon y minus y1 upon x minus x1. Simplifying that, you will get the equation of a line here. You can verify after finding the line. So, when x is equal to 1, if you substitute here x is equal to 1, y is 0. So, it is correct. When x equal to 1, 2 minus 2, y is 0. And also you check this point, when x is equal to 0, when x is equal to 0, y is 2, 0, 2 is another point. So, it is a straight line equation is y is equal to 2 minus 2x. So, the triangle is shown here, that is the triangle, its vertices are given. Note that the equation of the upper boundary is y equal to 2 minus 2x. The lower boundary of y you can say 0, the upper boundary is this. Now, the mass of the lamina, we have the formula of mass m is equal to the double integral fxy or rho xy dx dy. So, we know the limits of that triangular region, limits of the triangular region. X is equal to 0, x limits are constants, x equal to 0 to the maximum is x is equal to 1 here. They are the x limits. And y limits we have taken as the functions of x. The lower limit of y is y equal to 0, that is x axis, and move along y direction to reach the straight line. So, y is equal to 2 minus 2x, they are the limits of x and y. So, 0 to 1, 0 to 2 minus x, then this is given rho of x comma y is 1 plus 3x plus y dy dx. Now, I am integrating first with respect to y, because y limits are functions of x. So, integrate the inner integral, that is with respect to y. So, integration of that you can see here 0 to 1, integration of 1 is y, that is with respect to y, integration of 3x with respect to y, 3x is a constant here, constant with respect to y is y. So, 3x as it is, integration of 1 is y, plus integration of y, that is y square by 2. So, this completes the integration with respect to y. Now, substitute the limits y equal to 0 and y equal to 2 minus 2x. By substituting that, you can see here y is equal to the upper limit 2 minus 2x, 2 minus 2x. The lower limit is 0, that is neglected here, 2 minus 2x, that is the upper limit, plus the second term 3x as it is, 3x as it is. In place of y, you substitute 2 minus 2x. So, 3x into 2 minus 2x minus the lower limit is 0, so that is neglected. That is the second term substitution. Now, the third term y square by 2. In place of y, you substitute 2 minus 2x. So, 2 minus 2x bracket square divided by 2. So, this completes the substitution of the limits. Now, simplify before the next integration. 2 minus 2x as it is, multiplying the brackets, 3x into 2, that is 6x, 3x into 2x, 6x square minus. Now, first you expand and divided by 2. So, it is a minus b whole square type. 2 square, that is 4, 4 divided by 2, simplified to 2. Next, 2x whole square, that is 4x square, again divided by 2, it is 2x square, minus 2ab term, 2 into 2x, that is 8x, 8x divided by 2, 4x. So, that is the simplification before the integration. Now, add the like terms 2 and one more 2 here, 2 plus 2, 4, can see. Then 2x and minus 2x and minus 4x, minus 6x, there is a plus 6x here. So, x terms cancels, x terms there are 3, those cancels. Then minus 6x square plus 2x square, simplifying that minus 4x square. So, the constant term is 4, another term is minus 4x square. So, 4 minus 4x square, 4 is taken common, remaining is 1 minus x square. So, this simplifies to 4 into 1 minus x square, then integrate with respect to x. Now, integration of 1 is x here, minus x square integration is x cube upon 3, then substitute the limits. So, 4 into when x equal to 1, 1 minus x equal to 1 here, 1 by 3. The lower limit is 0, you neglect that. So 1 minus 1 by 3 is 2 by 3. So 4 into 2 by 3, that is 8 by 3. So that is the value of the mass of the lamina. M value is 8 by 3. Now go for finding the coordinates of center. So there is a formula x bar and y bar. The first one, x bar formula is 1 upon m, m is the mass. So x into fxy or x into rho xy dx dy. This rho is given. So same thing, the limits are same again, 0 to 1, y limits are 0 to 2 minus x. So x into rho is given 1 plus density function 1 plus 3x plus y. Now simplifying this before the integration, multiply by x here. So this bracket is multiplied by x, x into 1 x, x into 3x, 3x square plus x into y, xy. Now integrate first the inner integral, that is with respect to y. So integration of y, you can see here, m value is replaced here. M is 8 by 3. So 1 upon m means you reverse that, 3 upon 8. Now integration of x with respect to y, that is x into y, plus 3x square is a constant with respect to y means, so 3x square into y, plus x constant, y integration is y square by 2. So that completes with respect to y. Now substitute the limits here. 3 by 8, 0 to 1, x into y. So in place of y you substitute 2 minus 2x. So x into 2 minus 2x. Lower limit is 0, you neglect that, that is 0. So x into 2 minus x. Second term plus 3x square, y is replaced by 2 minus 2x, plus x by 2 is taken as it is. In place of y replace 2 minus tx. So x by 2 into 2 minus 2x bracket square dx. Now simplifying before the integration. So x into 2, 2x, x into 2x, so minus 2x square. Second term 3x square into 2, 6x square, minus 3x square into 2x, 6x cube it becomes. Here x by 2 into 2, or before you multiply, square this one, squaring this one and then multiply by x by 2. 2 minus 2x square is 4 plus 4x square minus 8x. Then multiplying by x, this becomes 2x, 2x cube minus 4x square dx. Now 3 by 8, there is a 2x and 2x, two terms, adding them 4x. Then 2x square minus 2x square, here minus 4x square, totally minus 6x square, and there is a plus 6 square term here, so cancel to 0. Now minus 6x cube is one term, 2x cube is another term, adding them minus 4x cube. So simplification becomes 4x minus 4x cube. So that is equal to 3 by 8. Now integrating with respect to x. 4x integration is 4 into x square by 2. 4 into x square by 2. That is 2 cancels, 2x square, minus 4 into x raised to 3 integration. X raised to 3 integration is x raised to 4 upon 4. 4 cancels. It becomes only x raised to 4. Now put the limits here. 3 by 8, when x equal to 1, 2, minus x equal to 1, 1. So it becomes 2 minus 1. Lower limit is 0. Both the terms containing x, so that becomes 0. So 3 by 8 into 1, it is 3 by 8. So x coordinates of the center is 3 by 8. Similarly, using the formula of y coordinates of the center, that is 1 upon m, m is the mass here, y into the density function into dx dy. So 3 by 8, m value is 8 by 3, 1 upon m means 3 by 8, 0 to 1, 0 to 2 minus 2x, then the density function is multiplied by y. So y into 1, y, 3xy, it is y square. First integrating with respect to y here, y integration is y square by 2, plus 3x into y integration is y square by 2 plus y raised to square integration is y raised to 3 divided by 3, putting the limits 0 and 2 minus x. So, this simplified to 7 minus 9x minus 3x square plus 5x cube, one substituting in place of y 2 minus 2x. Then integrating that, the remaining is with respect to x. So, 7 integration is 7x, then 9 into x integration is x square by 2 minus 3x square is 3x cube upon 3 cancels, x cube it is 5 into x cube integration x raised to 4 by 4, then put 0 to 1, when x equal to 1, then add them, simplify, it becomes 11 by 16. So, combining x bar and y bar, the center of the mass, it is the point, its coordinates are 3 by 8 and 11 by 16. So, in this way you can use the application examples using the listed formulas. Similarly, you can try the same type problem, finding the mass of the centroid of the ellipse with the density function is given. So, this is the elliptic region is there, find out the limits of elliptic region, then integrate using x plus y whole square. Now, that was about the double integrals, their evaluation procedures starting from the iterated integrals, then changing to polar coordinates we discussed, and change of variables, that was main. We can change the type 2 regions to type 3 region or type 3 to type 2 regions. So, now similar way we take the triple integrals, how the double integral was discussed. So, in this section we learn about the triple integrals and their applications. So, in triple integral just we defined as we defined in the single integrals for the function of one variables, go back to the one variable function and go back to the function of two variables, we define the double integrals. In that way we can define the triple integrals for the function of three variables here. F is a function of three variables. So, let us first deal with the simplest case here. F is a function of three variables, that is B is a rectangular box. In double integral we consider the region, rectangular region in the xy plane. Here we consider the rectangular box, the region is a solid region here. B is a box, its dimension when x varies from A to B may be length of the box, and y varies from C to D may be breadth of the box, and z is R to S, it is the height of the box. So, the region of the integration is a solid rectangular box here. You can see the picture, the region is of rectangular box type. So, as per the Riemann sum we discussed in the double integral case, first step is to divide this rectangular box into sub boxes. How to divide them? By dividing the interval AB. AB means the x limits are AB, dividing the interval AB into L number of subintervals, each interval of denoted as xi minus 1 xi, each of equal width of each subinterval is delta x. Similarly, the interval CD, they are the y limits in y direction, y limits divided into m subintervals each of width delta y. And similar way RS, they are the z limits in z direction, divide into n subintervals of width delta z. So, in all the three directions we divide them into sub boxes. You can see how it looks. So, every small box looks like this in the main solid region. This is the main rectangular box. You divide along x axis, y axis and z axis. You will get a small cube or small rectangular solid surfaces here. How to divide them? Planes through the endpoints of these subintervals parallel to the coordinate planes. Divide the plane parallel to xy plane, parallel to yz plane, parallel to zx plane. In that way you divide it, you will get a small rectangular boxes. So its coordinates you can see the point. Each sub box has a volume. This is important. Delta V, it is delta x, delta y, delta z. You take a small sub box in that rectangular box. Its dimensions are delta x length, delta y breadth, delta z height. So each sub box has a volume dV, that is a product of length, breadth, height. Then we form the Riemann sum, that is triple Riemann sum, how we did in the double integrals, double Riemann sum. So there we took double summations, here triple summations. One I varies from 1 to L, j varies from 1 to m, and k varies from 1 to n. This is the function f of x, y, z into delta v, that is dx, dy, dz. Where there is a sample point, this is the sample point in Bijk. This is the small rectangular box. You take a sample point in this box. This is the sample point Bijk in a small rectangular box. So it is similar to the definition of the double integral. We define the triple integral as the limit of the triple Riemann sum. How these mn in double integrals, mn tending to infinity, here you make them to infinity, L, m, n, make them to infinite. So that becomes the triple integral over f. F over the box is L, m, n, all they are tending to infinity. That sum, if limit of that sum exists, it is the triple integral of the function f over the rectangular box. Again the triple integral always exists if f is a continuous function. So you can choose the sample point to any of the point in the sub box. We have taken a one sample box here. So like that, collect all such sample boxes up to infinite number, add them, that gives the double integral, triple integral of f over the box. Instead of taking ij, jk, you can avoid them. If you choose it to be the point xi, yj, zk, we get a simpler looking expression comparing to the previous expression. The triple integral over f, function f over the rectangular box B is limit of Lmn tends to infinity. Simply it is f of xi, yj, zk, delta v. So like a double integrals, the practical method for evaluating the triple integrals is to express them as iterated integrals. How we did in the double integrals, they are converted into the iterated integrals. Iterated means integrating one by one with respect to x, with respect to y. Similar way we do it in the triple integrals. There are three variables x, y, z. So as per the FUBINI'S theorem we discussed in double integrals, there the iteration, it explains about the iterated integrals. F is a continuous function on the rectangular box, its dimensions are here. The triple integral is equal to, the limits are given, these are the Rs z limits, CD y limits, and EB are x limits. Integrate fx, yz in this order, dx, dy, dz. So the innermost integral is with respect to x, and then with respect to y using CD, and lastly with respect to z. So that process is the iterated integrals. The iterated integral on the right hand side of FUBINI'S theorem, as per that we integrate in the following order. So here the inner integral with respect to x means we know that while integrating with respect to x, keep the other two variables constant or fixed. So while integrating with respect to x, keep y and z are fixed or constants here. Then that becomes, after the integration with respect to x, that becomes the function of yz, because we kept y and z fixed there, that becomes the function of yz. So then we integrate with respect to y in yz variables, integrate with respect to y keeping z constant, keeping z constants, that becomes the function of z. After the integration with respect to y, the function becomes, which is the function of z. So, lastly integrating that function of z with respect to z using r and s, that completes the evaluation of the triple integral. So, there are 5 other possible orders in which we can integrate, all of which give the same value. So, as per the iterated integrals, there are 6 possible combinations of the integration of x, y, z here. So, one combination we have done here, first integration with respect to x, then y, then z. The second one is first integration with respect to x. So, second you can do it as z, then y, that is one combination. X, y, z, it is first combination. X, z, y, that is second combination. Then change first y, then x, z, that is one combination. First y, then z, x, the other combination. So, like that totally you will get 6 combinations, totally 6 combinations, all of them are giving the same value. So, we cannot simply change dx, dy, dz here, accordingly their limits to be changed here, not changing simply the dx, dy, dz, accordingly you change those limits. You want to integrate first x, take the x limits here. You want to integrate first y, take the first limits are y limits. You want to integrate z first, take the z limits first here, then which one is y, take y limits there. So, whenever the constant limits are given in triple integral, you will get 6 combinations of integrals here, 6 combinations, one is shown here. For instance, another one is given here. If you integrate first with respect to y, so dy is there. So, accordingly the y limits are taken here, y equal to c to d. Then with respect to z, second integration is then with respect to z. So, z limits are r and s. So, lastly integration with respect to x, its limits are a to b. So, whatever you do in serial order y, z, x, x, y, z, anything. So, accordingly you change the limits of integration and do it. So, all of them are giving same value. So, there are how many possibilities? There are totally 5 plus 1, 6 possibilities there. All possible orders you will get the same value. Now, coming to one example using the iterated integrals. Evaluate the triple integral where B is the rectangular box, its dimensions are given, x varies from 0 to 1 and y is minus 1 to 2 and z is 0 to 3. So, these are the dimensions, or you can take the limits of the integration. Solving this, so there are totally 6 possible, I told you 6 possible orders, any one of them you can use it, any one of them. If I choose to integrate first with respect to x, then with respect to y and then with respect to z, we obtain the result in this manner. You can see I took the triple integral of order x, y, z, x, y, z. The function is given x, y, z square, that is a function. It is given x, y, z. Then the limits of integration, x limits are 0 to here 1. It is taken the first integral limits. Inner integral is x, its limits are 0 to 1 here. X limits are 0 to 1, y limits are minus 1 to 2. So, next integration is with respect to y, its limits are taken second set minus 1 to 2. Third integration is with respect to z, its limits are 0 to 3. So, you want to change the order here, change the order dx, dy, dz to any other 5 possibilities. Accordingly, you change the limits of integration, then evaluate. So, in this way, the first integration with respect to x here. While integrating with respect to x, keep the other 2 variables constant. You know that y into z square is a constant here. So, only the integration of x, that is x square by 2, y into z square is as it is. Then put the limits x equal to 0 to 1 in place of x, not these two, putting the limits in place of x. So, putting x is equal to 1, it becomes 1, x square is there, x is equal to 1, lower limit x equal to 0, it is 0. So, its value is 1. So, that is why simplified to 1 into yz square upon 2. After putting the limits, it simplifies to yz square upon 2. So, after the integration with respect to x, it becomes purely a function of y and z. It should not contain any x, because we did the integration with respect to x. So, it is the function of the other two variables y and z. So, after ensuring that, now go further, next integration with respect to y. Doing with respect to y, keep the other variable z as constant here. So, z square by 2 is a constant, integrate with respect to y. So, that becomes y square by 2 into z square by 2, totally it is y square z square divided by 4. Then substitute the limits y equal to minus 1 to y equal to 2 and simplify. Put y is equal to 2 here, this becomes y square becomes 4, that is the upper limiting value, minus the lower limit y equal to minus 1 whole square is 1. So, 4 minus 1 it becomes 3. So, it is written 3 into z square by 4. So, the second integration is over. So, after the second integration, it should be a function of the variable which is left to integrate. It should not contain any y or any x, that you have to remember. So, it is purely function of z. Now, integrate with respect to z. So, 3 z square by 4 integration is 3 into z cube upon 3. So, 3 cancels, remaining z cube upon 4. Now, putting z equal to 0, z equal to 3. So, it is 3 raised to 3 is 27, 27 by 4. So, this is the value of the triple integral with the given limits. Even you want to change the order here, you can see the same answer you will get. Suppose you want dy first, dx second and dz later. So, accordingly you change here their limits, then evaluate one by one, you will get 27 by 4. So, this is about the constant limits. We can take any number of examples using in this way. There are totally 6 possible integration orders. Any one you can use for any type of examples whenever the limits are constants. So, this concludes about the integration with the triple integration with the constant limits. The next class we discuss about the triple integrals over the bounded by the surfaces. Thank you.